So we are the Depth of Waterway project. This is our final presentation. I'm Oliver Scholes.
I'm Daniel Stinson.
I'm Nicholas Gas. I'm Jay Creed. And I'm Keith Johnson.
Alright, so first things first, like, you know what they say the best for last. We're group 6. Came in first place in the 17th annual student research in the engineering category. So that was pretty exciting. So anyway, so our abstract, so the whole preface of this project was the Mississippi Delta bringing silt into the Gulf and dropping it here in the shores of Galveston. And especially with all the storm activity we get, it's always changing, and you're never really sure where the sand deposits are. So we set out to build an autonomous, started to be autonomous and then ended up being remotely controlled vessel that goes around and maps the waterway, so we have instantaneous updates on where those sand deposits are. So again, autonomous data collection, and also this creates less of a hazard for ships running aground and damaging marine life, and creates a safer industry, a cheaper industry, because like the Costa Concordia or the oil spill in Alaska, I don't remember the name of it, not the name of that ship, but anyway. So problem statement, kind of discovered it. The silt activity coming from the Mississippi and the dangers of running aground are catastrophic. And it's also catastrophic for the economy, like we saw in the Suez Canal just a month ago or so. And so also the damage to the wildlife can be pretty devastating. So our project goals were to design a remotely controlled vehicle that can automatically take data and then upload that to the cloud per se, and so we can access that data from the shore. And so it has to be rechargeable, easy to operate, and fail-safe data collection and storage, so it stores it on board as well as wirelessly transmitting it. So just some quick specifications. The length is about 25 inches and the width is about 12 inches, so that's what it originally was. And once we added the stabilization pieces of it, it got wider. Didn't get too much longer. But anyway, it weighs less than 50 pounds. It operates about 2.8 miles an hour. Get across the pool in about 20 seconds, so it's pretty quick. I couldn't catch it if I was trying to swim after it. And its max operating time is about 25 minutes. We didn't really test that because with the LiPo batteries, you're not really supposed to kill them all the way. It'll really reduce their lifetime. And the sonar max depth, it's like 100 feet or so. We didn't get out deep enough to do that because we don't want to lose it, because we don't know exactly how far the transmitter goes. So for the frame, the hull's aluminum, the top's plywood, and the stabilization's all PVC. And the electronics, so we have two 8,000 milliamp hour, 11 volt, 3-cell lithium ion batteries. Oh, and so the Raspberry Pi and Arduino operate off of a 20,000 milliamp hour, 9-volt power, like rechargeable bank that you bring on a camping trip to recharge your phone. And we also have a Blue Robotics ping sonar that takes the depth for us and uploads it to the cloud via a Raspberry Pi and Arduino with an LTE top hat. And so the transmitter is a Spectrum, like hobby style transmitter that I just had kicking around in my room. And that controls a AR410 Spectrum receiver that I also just had laying around. So we use that for steering and propulsion. And also two 40 amp thruster, or two 40 amp speed controllers and Hawk hobby thrusters that are mounted on the PVC that turn in thrust. Next.
So for the standards, so for the standards we saw was only for the United States Coast Guard, and it's pretty much an unmanned marine system best practices. We also found Army standards for our Army Corps of Engineers, state of Texas, Port of Houston and Port of Galveston, FTA regulations, BCC FR 105. And next, I'm going to talk about the constraints that we found. The first is the cost. If we have a small low cost of budget, then also is a constraint that we might not build it fast enough. and that's the same thing as quantity. If we don't have enough cost or the budget isn't enough, then we won't make it good. And if we don't make it good, then it won't make the customer satisfaction. And so resources also goes a cost, depending on the cost we have, is also the resources we have. And that's also another risk by losing a team member or not getting enough cost. And if we lose a team member, then the time that we have is going to decrease, and we're not going to fit it in time. And next, I'm going to give to Keith to talk about the engineering design.
So basically, our system is broken up into two parts. You have the mechanical, the vessel, the hull, and then you have the electronic parts. This task map is broken up into the propulsion system, the vessel structure, electronic configuration, and communication. And for the most part, Nico and Spencer were built with the vessel itself, and then me, Jake, and Oliver messed with all the electronics once we did it.
So for the bill of materials, here's our complete breakdown. We spent roughly just over $1,000, but we did have exterior funding included with that. So initially I planned us for a budget of around $700 from the university. However, I aimed for a budget of $500 spending that. So it'll be Nico talking about the concept drawings.
Yeah, so this is what the initial drawings from the beginning. As you can see, we have the red is the measurements that we have. There's pretty much about the same now. So you can see that the top, the right side, and the front side of the view. We also measured the sonar bit because we were confused, or we're not confused, but we were thinking where to put the sonar. And that's all for build plan. And I'm going to give it to Jay to talk about the design.
So the first thing I'm going to talk about is before we actually run the machine, we want it to be very simple to put together. So these are the steps to put it together to get it to run. So the first step, of course, is our electronics containers have to be mounted onto the lid. And we have a container on the top side and a container on the bottom side. The bottom side container is filled with our electronics, such as the batteries and the speed controllers. And then our top side is our Raspberry Pi and our Arduino. The reason why we had to separate these two is because on the top side, the antennas would not go through the wood when we were testing it. After that, we have to plug our thrusters that are from the pontoons. They go into, they connect under the lid, and then you plug them into our speed controllers, and then the speed controllers go into the batteries. After that, we would attach the lid to our hole. And in the hole, or to attach to the hole, we would bolt it down. Then attaching the sonar to the back of the ship, we created an L bracket for that, and that's where the sonar would attach to. And then the sonar cord then has to go to the top side to connect to the Raspberry Pi into our top side container. And then I will also talk about, so our construction progress, everything is constructed. So here's a little video of it going around near T-Dock. So the hull we were able to acquire, and then the lid and lid mounts, we cut the wood ourselves and treated the wood ourselves. And then the lid mounts are on the actual hole, and they're L brackets that we had to drill to a certain size and then drill the top of the lid. And then our stabilization system is these two pontoons you see on the outside. They're made out of PVC and are held by pipe clamps from the L bracket, or not the L bracket, the L turn PVC. And then getting the Raspberry Pi and LTE top pad put together, that was just connecting and soldering a few parts together so it would sit on top. Then on our Arduino, we have also added a timer to our Arduino for the Arduino to keep track of time. And this also required some soldering. The construction of code in Python in the Arduino and for the GPS. And this coding was this coding was found online with open source, but it didn't do exactly as we wanted. So of course we had to do some editing to get exactly what we wanted. Wiring the electronics, we had to wire solder extensions together so that it would reach the places we'd like. Let's see. Then attaching the motors or the thrusters to the stabilizers, we just used pipe clamps and a 3D printed square block that we created to hold them in place. And then I'll go ahead and that's it for that. And then I'm going to talk about our project schedule. So this is our first semester project schedule. Our Gantt chart kind of got cut off, but there was a lot of live editing last semester because of COVID being crazy. So I had to change a lot of dates. So in some places it doesn't look exactly right. But for the most part, first semester project was ideas and designs. And this, of course, our designs changed drastically because we found a aluminum hull that we could use. And that was kind of our base of our project. And then here's the project schedule for this semester. And this involves all of our construction and coding. And I, in this, put a lot of extra time in for problems we've run into. Gave us about a month and a half, I think, to figure it out, and we needed about that, so came out pretty good. Then Keith will talk about the test runs.
So throughout this whole development, we tested several factors of this. For the unit test, we actually tested 4 components: the vessel, the thrusters, the battery, and the sonar. When we first got the vessel, as Jake said, we found it. It was actually roughly welded, and so we went ahead and ground out all the welds and found the holes in it, and then we put putty in it that hardened like steel, and then we actually covered it with silicone, so that ensured our water tightness. For the thrusters, plain and simple, we just power them up, make sure we can get the point A to point B. The battery, just as long as it's stable and efficient, it powered our systems, that's all we needed. And for the sonar, at first we had a fish finder that Professor Coleman actually provided, or he had a contact to provide for us. That unsuccessfully was not what we needed for our data results, so we actually had to go on and buy another sonar. For our integration plans, the test plan, this is actually where we put systems together and actually tested them. The wireless, the LTE connection, gave us a few problems. I know we gave Jake and Aller a few problems. At one point, it actually stopped working. That's just because there were 2 programs on it, like pretty much were arguing with each other, and just the LTE turned off. So that they took them. Actually, Oliver actually had to give with customer support to fix that problem. Same thing with propulsion. We just make sure that our battery provided power through the thruster to get from point A to point B. And then our sonar, just make sure, actually the Blue Robotics gave us what we needed. So we went with that instead of the fish finder. For our load test, we tested some factors. We made sure that it was able to overcome the current, and if it's windy out, we tested all that these last few days were not really nice weather, so we did put it to the test. For the flooding, for the most part, it's very watertight, but we flooded it just to make sure it could hold water if that came to a failure, and it actually held pretty well. Pretty much filled up all the way and still floated. For both the propulsion and electronics, we just needed, I know, like Sid said, the LiPo batteries are not meant to die, so we just went for 20 minutes operation for both of them. The same thing with the charging batteries, which is 20 minutes. It was our base, which we actually made. And that's where it comes to the test results. Like I said, vessel is watertight, thrusters provide enough power to get from point A to point B. And we finally got our LTE connection to work, so it actually gave the data that we needed. And then we actually overcome the load test successfully.
So I'm going to talk about our actual test results. Well, it is very blurry, but so right here is our depths, and these are all timestamps so that we can identify a matching latitude and longitude on this side. So the format of this right now is a TXT file, and right here, it's kind of hard to see, it goes time, then distance for the sonar, And then on this side, we have our time, our latitude, and then our longitude. And we were able to check this with an aviation navigation program that actually Jonathan has on his phone. And we were able to see that it got pretty close. I had it out in my backyard, and it got it right where it was in the backyard. So that turned out pretty well. And then in the pool, when we tested it by itself, the sonar by itself, the accuracy was about 1 to 2 inches, not 1.5 inches off. And that's about it for that.
So the product requirements, what was our product meant to do? So we wanted it to do untethered operations, so you didn't have to have an Ethernet cord or some sort of cord that you're limited to. Precise data collection, so you know exactly how deep it is at a certain location. Wireless data transmission, so you can upload and download from the unit itself and then control the unit elsewhere. And then unfazed by currents and winds. So, you know, the channel out there has quite a strong current in it, so we wanted to be sure to avoid that. So for the customer defined needs, so this would be more tailored to what whoever is buying the unit or using the unit. So in this instance would be the university. We need it to be easy to operate, so almost anyone can use it with very little training. Depth and GPS data collection, so you know again the location, the depth at a certain location, and translate data to a graphical friendly interface. So our achievements, as Daniel mentioned, we got first place in the symposium, and we also have a functional device that is ready to use and can go out and collect data for you, and you can have it on any computer at any time. The top issues we faced throughout the time was shipping and delays, and then also we had a week off from the winter storm. Incompatibility issues with the Blue Robotics first-party program. On their website, they never mentioned the system requirements that you would need. They only mentioned the software requirements. So the issue came in place with the architecture of the CPU on the Raspberry Pi was incompatible with what they wanted. They wanted Intel-based CPUs. For the LTE top hat connectivity errors, as Keith mentioned, we did run into quite a few issues with the modem on the LTE top hat that pretty much tells the SIM card, hey, I need to connect to a satellite and come to me. There was pretty much 2 drivers installed at one time that were giving conflicting information to the modem. So that at one program would tell it to start doing something, then the other one would say, hey, no, stop, I need you to do something. And it'd be a back and forth until it just quit. And luckily the 6Fab customer support was very helpful in getting us expedited support because we were a university project. And then for the MATLAB contour map, Jake, if you want to explain more on that.
So it turned out I didn't have enough time to finish it off, but the biggest issue I ran into was the amount of data points that were taken. Having the program decode all of that, I just didn't have enough time to do that. So
we can have a look at it.
And then, so for our team member contributions, we all work equally pretty much on the nuclear reports and the critical testing part. So the flotation part, taking it for a test drive, stuff like that. So for me, and if everyone wants to say what they did, so coding for the Raspberry Pi, the LT, and the GPS, finance management, the vessel assembly itself, for electrical system development and installation would be the batteries, getting everything, make sure it's all going to be working nominally, and how long can stuff last. And then vessel waterproofing and demonstration preparations, so painting and such.
So I did some coding for the Raspberry Pi, the LTE GPS, Arduino, and I also did MATLAB, or some MATLAB. I helped with the vessel assembly. I helped with the electrical systems, and then I also helped with the final demonstration and waterproofing the vessel.
Yeah, so I pretty much did my hand in vessel assembly, Also, the sonar came with a mounting hardware that we were trying to use, but it didn't quite mesh well with our hull because it's meant to mount onto a flat face, and the bottom of our vessel is a V shape, so the sonar would be hanging at a 45, which is not what we needed. So you had to fabricate like an L bracket that had the right holes and the right dimensions to actually bolt onto the sonar. So I did that. Did some wiring fabrications, like soldering extensions, and then all the propulsion and RC stuff is all mine. And I set that all up, and it's great.
And then I aided both in vessel assembly and arguing on the electronics.
And I also did scouts on the vessel assembly as well.
All right, so what's next? So if someone next year were to take our project and then beef it up, autonomy would be really cool if you could take it and tell it to find a GPS point, like go here, stop, take data, go somewhere else, and draw out a cool map. And then also the data analysis, so uploading it, having a code to take that data file, process it, and put it into the contour map. So you're looking at a map as the vessel goes around. And then finally, to like go back to why the project started would be to open the distribution channels for the data. So to let people know what we find when we take the data points. So the original problem was to get this to seafarers or people that travel the waterways often. So we'd have to open those channels and send the data out for a price. Because why do it for free in this capitalist world? But anyway, so send it out and make the industry more safe. Questions?
How far out you want it? How far out?
So we just got a latitude and longitude, and it's taking depths right now. 2.2 meters. Went up. Where are they at? Oh, they're coming back. I thought they were still going out.
This is a dedicated scientist right here.
He
was headed for the water.
I was about to
with the notebook in hand.
Yeah, 1.4 meters. Oh yeah, we're here. Yeah.